Autodesk Simulation portfolio. So let's have a look. So I will launch it once everybody has had a chance to join, so that everybody can see the typical audience. Large audience, so I'm going to give, we have plenty of time. We have allowed 1 hour. It's going to take me approximately 30-35 minutes to go through, and the reason why I have put an hour is I'm hoping that people will have questions they may want to ask David, who just spoke to me 2 minutes ago. If you feel comfortable typing in a question in your local language, Swedish and Norwegian, then by all means do that. If we do not get time to go all the way around for any question and answers, we will then respond to you after the event. So it's entirely up to you if you feel comfortable. Type in your question in the local language or English. Okay. I think we'll just wait for a couple of more minutes. If anybody's got any questions, you are more than welcome to basically type them in. Fantastic. Okay, I think just 1 more minute. I see more people are joining us. So again, if you just joined us, I would appreciate some input on the poll. Just give us an idea of what you're currently using. Thank you. Okay. And obviously, if you want to type in anything, just can anybody type in something in the chat box to say you can hear me loud and clear. I know David said he could hear me, but you want to make sure that in our communications or anything like that, just put it in the chat window, and any questions you may want to ask me regarding the software and the presentation, I would suggest you put them in the questions. But it doesn't matter now, but I think thank you. It looks okay, guys. I think we're going to start. So I'm just gonna close the poll just to show everybody what the audience is like. Can I see it? Okay, I'm just going to share it now. Can everybody see the? So we have a pretty big audience from the inventor stress environment, which we suspected, and we have a small audience from the frame analysis. This is the beam analysis software or structure analysis, and then we have the inventor Nastran, which is the book of the presentation. And then we would have some newbies, I guess. I would guess if you're not using the Autodesk Simulation software, you're probably using some other software. That's also okay as well. Fantastic. Again, thank you very much for sharing that. So a little bit about myself. I have been working with Symetri for over 10 years. I have had exposure with various simulation tools like MSC, ANSYS, and Algo, which you may not be familiar with. Autodesk did acquire that technology a while back, and obviously all the Autodesk simulation software, which we're going to talk about today. And obviously, if I have trained any of you in the past couple of years and weeks, I have authored books on Autodesk simulation software, on Nastran, linear, non-linear, stress analysis, which is also frame analysis, and there's also another book on dynamic simulation, which we are not going to talk about today. So enough about myself, and let's go through what the plan is for the next 30 minutes or so. So basically, I am not a big fan of PowerPoints, but I think the best way to demonstrate a lot of my ideas and tips, I will be using PowerPoints. So we're going to go through Inventor Stress, which is a book of the audience, some 10 tips on that. We're going to talk about some tips to keep our friends who use frame analysis happy. and then we're going to go through linear and non-linear. Some of the tips in Nastran will also be useful for inventor stress. Now, I thought we have a huge audience here, and I just want to have the opportunity to show you a small presentation on a product called SimSolid. Now, all these tips and tricks we are talking about, we have to do them because we want the software to be able to mesh it and be able to run it and have the run times pretty small. Now, SimSolid does not require any tips and tricks. It's a very fast solution and it just works. So that is for 10 minutes towards the end, I would like to show you an example, and then you can relate that example back to how you think you could do that in Nastran or Inventor Stress. And then hopefully after that one, we'll have ample time for any questions you may have. But if you think of a question, if you based on what I'm showing you, please type it in the question so that we can go through together. Okay, so let's first have a look at the Inventor Stress, which is primarily used by many of our customers even today. So even though you're using Inventor Stress, you do also have access to Nastran as well. So you have both softwares. Okay, the first one I would like to share is the split command. Now, I have spoken to customers, many customers, and when you want to apply a load on a certain portion of your component or an object, I have seen customers actually creating small features. What I recommend is not to create small features because the software has to mesh it. There is a chance that you might get high stresses or you may get mesh failure. The better option is that you should use a split command to split a face, and that you'll have a nice mesh around that area. You can apply this, also applies to Nastran as well. Now, this is my favorite. Even I have seen customers doing full models, and some customers are familiar with having to split the model in half a model, half symmetry, and also a quarter model and 1/8. But I've never seen any customers who have cyclic symmetry, or you have components which have a cyclic symmetry, because the perception is that we can't do it inside Inventor Stress. This is an example here which we have about 10 blades, and you can see there if you do the whole fan, it's about 12,000 elements, and if you do one blade or one portion of the fan, it's almost 1,600 elements. So you can do it. As a tip, I suggest you split it, trim the component into one, and then you simply do a pattern to make sure it looks like the whole fan. So cyclic symmetry, yes, you can do that inside Inventor and Nastran, because it doesn't say cyclic symmetry. I know some softwares like ANSYS, MSC, the Abacus will have a terminology saying cyclic symmetry. So you can do it. It has been done with many of our customers. Like this is from a Halifax fund in the UK as an example. And the other one, which I get asked a lot by customers, is can we apply torque to bolts inside Inventor Stress? Well, the answer is we don't have a button in Inventor Stress which allows you to apply a torque. And one option is, this is an example again from a customer in the UK, what you can do here is you can actually break the bolt into half along its shaft, and then you can apply a load where you cut it, and that way it will give you some sense of preloading as well. You can, if you want to see the whole bolt, then you can split the bolt and then apply a load in opposing directions, as you can see in this middle diagram here on the left side here, arrows opposing one another. So it can be done. Okay, the next one is more to do with inventor commands. And basically here is that when you have a weldment, I don't know how many people listening to me here use weldments inside Inventor. If you are doing it, then I would recommend that you shrink wrap it into a single component. The benefit of that method is that you're not going to have too many contacts, and then you may not have any mesh failures, because when you create welds, for example, in Inventor, you have sharp edges and very small features when you have a weld around a radius, for example. So I would suggest shrink wrap it into a single component. And I would like to emphasize further that I would recommend not to use weldment assemblies, because the picture on the left hand side, you can see there is a lot of red. If you can just barely see it, we have a very high stress, and picture on the right, the same model without the welds. So I would recommend not to use weldment assemblies, and I would guess not many customers use actual weldments, because it takes a long time to create the welds, I guess. So I guess it's a time thing as well. And one great tip I would recommend is that I would suggest that if you're not using weldments, now you can see here we have a box section and we have another box section basically joining. I would suggest that you prepare the geometry and actually suppress the round as there was a weld there, because this will yield better results, everybody. So this is another tip I will recommend to actually model the weld as part of your CAD geometry. The next one is inside Inventor Stress, you also have the ability to do models with shell elements and solids. So this is a simple tube. And then the big question is, when should you use shell elements? Now, there's no right and wrong answer here. I would suggest that anything with a ratio of 1 thickness and 30 length or higher, you should consider using shell elements. So you can see here, obviously I've not compared the results here. Shell elements will yield a better result than solids. In solid, you can see here also you need to do or create a lot more elements in solids. Here you can see that on the left side, we have almost 12,500 elements, and on the right hand side, we only have 1,300 elements. So you can see here, there is a benefit to do it with shells, less elements, and also more accurate. Okay, again, on the topic of shells, when you have a component which has multiple thicknesses, like a component here, the top plate is 20 mil thick, and the bottom box section is 8 mil thick. If that was one component, then inside Inventor Stress, the mid surface is like a magic button in mid surface. You click on mid surface and it converts your solid component into a shelled model. Now, if you do that and the object was as one, then you're probably going to get a wrong thicknesses. So the best way to do this is that you convert your component into multi-body. So the bottom half is basically going to be 8 mil thick, and the top plate is going to be 20 mil thick. So when you go into Inventor Stress and you click on mid surfaces, you will end up with creating two surfaces, as you see on the right hand side. So multi-bodies is great if you have if you want to do surfaces with multiple thicknesses. And just two more to go on Inventor Stress. Then you see here, if you had a C-section, as you see on the left-hand side of my model, you see that when I click on mid surfaces, it creates a gap between the top and the side. As you can see here on the left side, sometimes this is very common when you do mid surfaces, because the object is basically tapered as well, and it has a radius. So the one way to do this is not to use mid surfaces, but to use offset surfaces, and you can basically then define whatever thickness you want. This is probably ideal if you are going to have the same thickness all the way around. So the picture on the right hand side, you can see the whole thing is connected. And I think my favorite here is this. I do appreciate that Inventor has its automatic convergence button. Now, everything I'm saying here is my own personal views on the software and how it works. The automatic convergence button is great, but when you have objects which do not have a smooth transition, the automatic convergence will never work. And I would recommend that try this approach, is to change the mesh in the area of interest yourself and half the value every single time to see whether the stress is going to change. So this is an alternative to the automatic convergence. Okay. I would like to remind everybody, as I'm doing this, if you have any questions, anything, any comments which I haven't mentioned, just please put them in the questions box. Okay, now let's move to frame analysis. Obviously, this is an awesome product in my opinion. It's based on the robot software, which is available as part of the AC collection, and it's used by a lot of structural engineers. Now, it's absolutely amazing for framework type structures. So the question then is, there is a tube which we're going to basically fix at one end, and then we're going to apply a load at the other end. Now, would you do that using solid elements or shell elements? Or the other option is to do it as a beam element. Now you can see on the right hand side, the hand calculations tells me it's 296. What's the value we need to work towards? Now you can see the picture on the right, on the left hand side, we have a stress of 283. And if you look on the picture in the middle with the colorful line, you can see the result is absolutely spot on. So when you are doing frameworks, I would consider to the customers here on clients that to consider using beam analysis as well, because the software absolutely is amazing how it works. And beam elements are absolutely accurate. And one more tip, when you're doing beam elements, there is no need to change the mesh 3 times, 4 times. You just refine the mesh and run it, and you have a solution. Okay, now some of the guys who are already using it, and if you use a frame generator, for example, then I would recommend not to do the notching and mitering, because if you do the mitering and notching, if you look at the image in the middle, you can see there is gaps between the green lines, which are the beams, and there's like a red line between connecting. That's what happens when you do the mitering and notching. The model does not look as clean as you would like it to be, basically. So I think what I'm suggesting is do not do the mitering and notching, and then you will basically get a nice connected beam like the image on the top left-hand corner. I'm not sure if you can see my mouse moving. I hope you can, but that is what is going to demonstrate. So don't perform the rigid links. The question is, well, you haven't tested it. So why would you start mitering and notching and then realize afterwards I need a bigger beam or a smaller beam? So that's one tip. And then this is a very popular one, guys. When you create frameworks like this, you have moments at the connections. It's very, very easy inside of Inventor frame analysis to use beam releases to be able to have pinned connections in your structure. So the image on the left-hand side is not a pinned connections, it has moments at the connections, and the image on the right-hand side, you can see there straight away, we have a pinned connections as there is no moment at the joints. So that's a very popular one. And this is interesting. We have a simply supported beam. And what happens is when you have two pin connections at either end, you get a warning. And the warning shows you on the bottom left-hand side. So how do you resolve that? Well, what you could do there is you could actually remove one of the pin connections, and then you can use something like a custom constraint. The reason why you get the warning is because a pin connection only fixes in the X, Y, and Z degree of freedom, and it allows a rotation about X, Y, and Z. And what's happening basically is the tube or the object is spinning around its own axis, in this case, the X-axis. This is why we fix the X-axis using custom constraints to get a more stable result, and the results are both identical. So custom constraint is very valuable, as you will see on my next slide. If you want to create a compression only constraint, for example, let's take a chair. The chair basically will be, the legs will be under compression as you sit on it, but when you try to sit on the side of it, there's a tendency for the legs to move away from the floor. And that's what I mean by a compression only constraint. And you can create that using this clever custom constraint. Okay, so these obviously, so these topics, these tips have been taken from my book, The Inventor Stress and Frame Analysis. It is available on Amazon. And on the right-hand side, we still do a lot of training courses around Inventor and frame analysis. And if you happen to want to learn more, then the book is actually provided as part of the training course again. If you just want, if you don't have the time to attend, then you can get the book from any Amazon site. And everything I have covered on there and more will be available in the book. Okay. Right, let's have a look at Nastran. Okay, so I'm gonna first of all start with the linear analysis, which I think the bulk of the customers here are using. And then I will also mention some of the non-linear tips as well. Okay, right, the first one. Now, I'm not sure what version of Inventor you are using. I think version 2022 onwards, there was something called a model state. And when we are analyzing objects inside Nastran, we want to make things simple for two things. One, it meshes nicely, and secondly, some of the features have no consequence on the analysis. So it's very, very easy to switch between the model states inside Inventor. And once you have switched the state, then when you go into Nastran, it will work on the active model state. I think they were used to be called level of details in the previous versions, which worked in a similar fashion as well. Okay, now I don't know if you've experienced this before. When you are doing analysis inside Nastran, what tends to happen is that every single command is available from the top. This is the only command, concentrated masses, which is not available on the panel. So to find it, you have to expand the model tree, and under idealizations where you find your solids, shells, and beams, you also have concentrated masses. Click on new, and then you can have a command, and then you can start copying it once it's in the analysis tree. So that's the only command, as far as I know, which is not available and is hidden in the model tree. Okay, so this one, there's a lot of text on the slide, so I will try to explain what I mean by here is that there are three options when you create contacts. One is automatic, which is very, very popular with solid elements. Then you have manual contacts, and then you also have solver contacts. Now, solver contacts are absolutely brilliant. The only downside is that when you create automatic contacts, you will see contact pairs. But when you have a large model, I don't think anybody will check which contact pair belongs where. The solver contact, basically, in my opinion, is very, when you click on it, it will only say one contact, it's a solver contact, and it only will activate once you press run. And I have found out the solver contact is more robust and it runs very quickly as well. The only exception is that when you have lots of sliding and separations, then a manual contact or automatic contact will work well. So I think for shells and mid-surface extractions, solver contact is your only option. Now this one seems to be very technical. So when you change certain things, like for example, I want to be able to use all my cores on my machine. I don't want to use 4, I want to use 16, I want to use 32, but the problem is every time you open a new file, you have to change the parameter value to 4, to 16, or whatever you want. Now, this is basically a .ini file. It controls all the parameters in there. If you want the ability to change the parameters in there, and then every time you open something, a new file, guess what happens? It will run all the cores. For example, file spec, it'll open. So you can actually make all the settings in your .ini file. This is under the everything else where Nastran files are. If you think you would like to do that, then get in touch with us and we can guide you on how to set the parameters, the ones you use all the time, then it will be set. And also, I think it's different paths depending on what version of Nastran you're using. I guess everybody here is using 2020 and beyond. So this is a very powerful tip. And if you have tried to create bolted connections, one of the tasks which is very, very tedious is that to create a bolted connection properly in Nastran, then I have recommend to clients and customers is that you have to split the surface around the hole where the bolt and the washer goes. Otherwise, you're going to end up having high stress concentrations if you're only going to pick the edge of the hole. Now, that can be a very time-consuming process when you have 20, 30, 40, 50, and 100 bolts in there. So one of the options is you simply don't split the faces, create washers, and bring the washers through into Nastran. You will have a bonder contact between the washer and the plate, and then you can create the bolt head and the nut head by picking the washer surfaces on both sides. And I think that's a lot quicker than actually splitting your faces. Okay, now this is also another method. So when you have thin structures, like for example here an I-beam, then what tends to happen is that when you go into Nastran and then you click on the fine thin bodies or use a mid-surface command, you'll probably get gaps between the top and the middle surfaces as you see in the left image. Now, if you don't want to do that and you don't like it, then the only option, I'm afraid, is to create a surface model inside Inventor where you have the surfaces touching and then you have no gaps. And also the benefit of doing that method is you don't have to create contacts because you have the nodes merging and it creates is connected. It's a bit like having a multi-body. Whereas on the image on the left-hand side, you would have to use solver contacts with a max activation distance specified, which will cover the biggest gap. Okay. Now, if you have done any beam analysis inside Nastran, then one of the things which is very important is that a tube, maybe not so much. When you have angled plates, C-sections, and I-beams, you want to be able to see the orientation of the profile so that is in the right orientation. And the way to do this is that you right hand click on elements in your tree under nodes and units and click on display cross section. One word of warning, do not refine the mesh before you do this process. Use a very coarse mesh, then click on the display cross section. And then you can see the profiles on the right hand side if they are in the correct orientation or not. Then just like frame generator, you can then change the angles to suit your needs. Okay, now this one, now inside, inside Inventor, for example, let's just compare something. When you have a mesh and you have a result, then you get a stress result. Then you go and change the mesh again, and then you look at the result again. Okay, in an ideal world, what we are looking for is a 10% difference in the results. Now, that is the only way you can do things inside Inventor Stress. But inside Nastran, we have something different, maybe better, that you have a choice now. You can do the same thing like you do inside Inventor Stress. You change the mesh 3 times and look at the results and see if the results are becoming flat and they're not changing too much, or you have a choice. You can basically, in Nastran, there are 2 sets of results. One is called a corner and the other one is called centroidal. The both results should be the same. And what happens is that there is a small amount of discrepancy because the centroidal results, imagine a square. In that side of that square, the centroidal value is in the middle of the square and the corner values are on the corner of the square. As the square gets smaller and smaller, eventually you'll get the same results. So if you mesh it once and then you want to understand, do I need to mesh it again? You look at your corner results, then you look at your centroidal results. If the results are very close and within 10%, then you don't need to do it. You only need to do it if the result is outside 10%. So it's another clever way to find out if my mesh is good enough and if my results is good enough by comparing corner and centroidal results. Okay, and this was very strange. 10 years ago, my first support call I received is saying that my stress value and my safety factor value is incorrect. What was happening basically was that when the customer and the client looked at the stress value, it was von Mises based on corner. When he divided that value from the yield material, it did not match the safety factor on Nastran. So what I'm trying to say is if you are interested in safety factor plots, the value is looking at to calculate the safety factor is not the corner value, it's the centroidal value, as you can see on the picture on the right hand side. But then again, I've not seen many customers who actually use a safety factor plot. But if you are, then make sure the result is based on the centroidal value and not the corner value. And finally, on the linear stuff, this is a very frustrating sort of what's the word? I think everybody here, not everybody, most of you will have a scenario where you have a stress or a hotspot or stress singularity or localized yielding, whatever you want to call it, where the stress is above the yield and it's a little dot somewhere. So what do? Do you ignore it? Do you use your experience? Do you use your intuition? Or you get worried? The good thing about Nastran is that there is a very easy process that you can run it as a non-linear static analysis based on the stress and strain curve you see there. So the picture on the left-hand side is my stress singularity. You can see the stress just about almost 500 megapascals, and the image on the right-hand side, it never goes beyond 255. So the only thing I'm looking for here is how much strain there is. So you do have a choice that you can run it as a non-linear analysis to determine whether it is whether the stress is important or not. And again, everything you see on there has been taken from the Invented Nastran book, available again on Amazon. This is our most popular course. We literally do this every 2 weeks, and the course is based around all the linear capabilities inside Nastran. And again, if you had time or you would like to attend, you will receive a complimentary book by attending the course as well. Okay, so now the final tips. Is on nonlinear. So I'm not sure how many people here are doing nonlinear. These were from my class from Autodesk University, and I thought it might be worth sharing that with everybody here. If you are interested in doing nonlinear, maybe you want to do the last thing I mentioned, how to avoid stress singularities. So the first and the most important one is you have the ability to change the element order. Now, when we're doing linear analysis, it's parabolic, never change it. But for the nonlinear stuff, we change it to linear analysis for two reasons. One, it runs quicker, a lot quicker, I mean, to converge the results. And secondly, I don't think it makes a huge amount of difference whether you have parabolic and linear in terms of results. But it does run a lot quicker. So that's the most important one. Also, if you are using surface models and they are touching, then I suggest you use this button called continuous meshing. I'm not sure how many people use that, but the surface models have to be touching. You can't use this if you use the fine thin bodies or mid-surface buttons inside Nastran. You have to create the models from scratch to be able to use them. Now, in the earlier versions, I'm not sure if you had 2018 and 2019, when you run a non-linear analysis, what tends to happen is that that area where it says number of increments, that usually populated to 10. So engineers then decided, well, I'm not going to use 10, I'll use 15, I might use 8, I might use that. But the thing is, as best practice, and in the later version software, it's blank. Do not specify any number of increments. Let the software work it out. Because it will be a lot quicker for the software to work it out rather than you specifying. The only benefit is if you put 10 there, it probably gives you a load increment every 10%. So 10, 20, 30, 40, 50, 60, 80, 90. If you leave it blank, the tendency is it might go to 10, it might go to 30, it might go to 60, it might go to 80. So you can have a look at 60% of the loading criteria. That's the only downside if it's a downside, but leave it blank. And this, I have had customers telling me that when they define a stress and strain curve, and when they look at the results, why are the results higher than my stress and strain curve? They don't follow the stress and strain curve. The reason being is that don't look at your von Mises stress results. Look at your equivalent stress results, and the stress values will follow your stress and strain curve. Okay. Now this is the one I mentioned very briefly before. Every time you open a file and it runs, by default, I think the number of processes Nastran uses is either 2 or 4. I'm just guessing now. I should know this, but you have the ability to change it to whatever cores you have available on your machine. Now you have to do that every time you open a new file, unless you go and change your ini settings, the tip I mentioned in my linear analysis tips. Okay, now I did mention to use the split command to apply the load. Again, use the same process. Use split face at the areas where you have contact. The reason being is that when you define local mesh control, it does not pick a bigger area than required. You only want to pick the area where the thing is going to impact. What this does, it does two things. One, it creates less mesh elements, and secondly, it will create a lot less contacts. Contacts are one of the reasons why the software can take a very long time to run. Okay, now this is something that I don't think many people may have had experience with. But if you have been doing nonlinear analysis and you get strain around 10%, then it's okay. If you get higher strain than that, 20, 30%, then you might realize that the software is taking forever to run, or it may never complete. So if you have very high strains, this is where the shape does not look like the shape it started from, then I would suggest that you use explicit solvers, which has been available in Nastran, I guess, since 2021, I think. And if you basically are running a non-linear transient response analysis, for example, like a drop test, or you have a time-based loading, the problem is that there are too many settings you have to type in, and one of them is structural damping and what on earth is dominant frequency. The dominant frequency basically is the first mode of your modal analysis. So if you want to find out what it is, do a modal analysis first, and then specify the value, and then hopefully it'll give you the value, and the damping value is typically anything from 3, 4, 5%. So that gives you an idea what is happening. Okay, and one of the reasons why we do a nonlinear analysis is that I'm interested in, or the customer's interested in, how much deformation has happened when the load comes off. And if that's the case, then I would suggest that you need to run two subcases. In nonlinear analysis, each subcase is related. In linear analysis, they're not, they're independent. So in this one here, in loaded 1 subcase, a load has been applied. In unloaded subcase, load has come off. And only gravity has been applied, and then you can see the permanent deformation when the load comes off. And finally, when we are running a time-based analysis, we have to specify time steps. So on the picture on the middle, you see a time step of 0.0005 seconds. That's a very small time step. If you want to run it for a long period, then you'll be running for a long, long time. So you can create, again, different subcases. The reasoning here is different. You want to create different subcases so you can specify different time steps. So you can see the picture on the right-hand side, we have a 5 millisecond time step. So you can have different subcases to do this type of stuff. And again, if you're interested in learning more about a non-linear analysis, there is a book available which you can also access. And also we are running advanced courses on Nastran if you have time and you would like to learn more. Now, so that is the end of my tips. And before I show you a very short presentation on SimSolid, so everything we did there and the tips are helping us to create a better mesh, run the software a lot quicker and faster. Now, before I do that, I have a very short poll, which I'm hoping that you guys could provide some. So based on your inventor stress experience, your Nastran experience, I'm hoping that you can give me some sort of indications of how long you spend on creating well, setting the model up, simplifying it, preparing it, running it once or twice or 3 times to get the final result. So we'll wait a minute or so that I can have a breather from talking. Okay, so I'm just going to share this. So we have 60% of the voting here. So let me close the poll. And can I share it? Yes. Okay, so this is not 100% of the audience. So we can see here that almost 50% of the audience here will spend more than a day, around a day or more to get any sort of results. Okay, so just bear that in mind. Now this is where things can go horribly wrong. Can you still see my screen? Yes, you can. Okay, so everybody should see a PowerPoint slide around SimSolid. And basically the top phrase there put down there is simulation made easy. Now literally just big structures, it does not care about features, it does not care about complex geometry. Trying to mesh that picture on the right hand side, extreme geometric complexity, I don't think any software will do that. And then when you get the picture on the bottom right hand side, when you get lots of little transitions, you will get lots of mesh errors. So these are where its strengths are. And then here we are not suggesting that you replace Nastran. SimSolid is a complementary solution to help you make rapid decisions. And these are the areas we are focusing on with our clients. One is complex geometries where traditional softwares like Nastran, MSC, ANSYS will struggle. And these are 3D printed objects, lattice structures, and then my favorite is the second one, large scale models, lots of frameworks. How would you do that in Nastran? I guess it will take a long time. And also we can work on bolted. I don't know how many people here use bolt connections. We can't use bolted connections inside Nastran. We create our own bolts. But the example I'm going to show you very quickly, I know this is not an Altair presentation, it's Autodesk, but I just wanted to show you, share with you something that you may think about. So I'm just going to show you, this is a platform. Okay, where is it? There we go. So you can see here, I have a very detailed, complex model here, which is very big and large. Now, you try to run that in an Nastran, I think it will struggle. So we have to start thinking about, well, first of all, remove all the bolts, remove all the handrails, remove the ladder, even remove the platform in the middle, because we don't need that. Because the reason being is we're thinking about what it may not mesh. So I'm going to leave it as it is. It has material already assigned to steel, that's fine. And what we're going to do here is I'm going to run a model analysis. Before I do that, just like Inventor, like Nastran, we go into here and pick the automatic button and we press OK, and it goes away and creates contacts. Okay, so it's created the contacts. So let me go down here and it has created almost 1,300 contacts. Now, I don't think anybody here, even in Nastran Inventor, will go and check them one by one and see everything's fine. And one other thing I'd like to show you here is this one. If I go and zoom into here and right hand click and show you there, you see this is it recognizes that is a bolt. It creates a special contact, bonded and sliding. So you don't have to go and change the contact types. as you would do inside Inventor and Nastran. So it's very clever from that perspective. And now what we're going to do here is, I'm happy with that, I think. I'm going to check if there's no disconnected groups. Okay, that's fine. I'm going to do one of the things you can do in Nastran, and it's also in Inventor Stress. If you have a large model, you can basically run a model analysis like I'm going to do here, and you can do that to check if anything is not fully connected. So you can do this also in Nastran and in Inventor Stress. The only thing I'm going to do here is I'm going to fix the bottom of the platform. So I'm going to zoom in here, this one, and the good thing about SimSolid is that I can pick all 6 constraints in one and still be able to check the reactions on each individual face. Okay, there we go. So remember when I mentioned one of my tips, converge mesh 1, 2, and 3. Watch this. At the bottom left hand corner of my screen, I don't think you can see it, it goes through 3 iterations automatically by default. So it's going through 1, 2, and 3. So you could say it's going through a mesh convergence process itself. And how long do you think it would have taken if you managed to get that in Nastran and Inventor Stress? If you managed it, probably take a long time. I think the biggest problem you're going to have is it doesn't mesh. So let's have a look at the displacements in my model analysis and see if it's all connected. This is a quick way to check. So this is one of the great tips for large models if you want to check if nothing is connected. So I'm going to go through all my mode and see what's going on. You see there, even though it's connected on the side, it's not fully connected with the bottom plate. So that's fine. Keep on doing that. Also I have another problem here. Them two here as well. So this is a very quick way to check if nothing is connected. So I'm going to finish this. I'm going to go and I can increase, as you would do also in Inventor, increase that one. I'm not going to increase that one. I'm going to show something different. I'm going to go in here. I'll do a group connect between this plate here and this one here. Not wrong one. So delete that one. It's this one I want. And increase that gap to 2. Find connections. There you go. It's connected now. So let's go to the other side. And the reason why it didn't connect is a gap between it. This one's fine. It goes through it. So let's do the same thing again. I'll use a third option this time to show you what else you can do. And again, make it 2, and then find connections, press OK. Oh, I forgot to do that one, so let's do that one again. This one and this one, make it 2 again, find connections, and I'm happy with that one. So let's just make sure that everything is fine. We'll run it again, and this, remember guys, we are running it 3 times. The software literally is super fast. So what I'm looking for here is if everything is connected. And down here, you can see everything's connected. And very quickly, because of time, I'm concerned is I'm going to run a structural gravity test here. I'm going to copy that constraint into my structure. I'm going to apply a gravity load on here in the Z direction, which is -1 and 0 here. And then I'm going to run this again. Did I copy the constraints? Let's see. Yes, I have the constraint. Let's run that one now. And I want to show you what happens here, that you actually will get a stress value and you also get stresses and forces in your bolted connections. Okay, so this is a good time, guys, to start typing in your questions if you have any. And I'm just almost finished here. There is my model. Everything looks okay, but the one I want to show you here is this. This is a whole table of every single bolt in there, which I can look at. And the one thing I didn't show you here very quickly is you can actually put, just like Nastran, you can put bolt preloads. There you go. Look, pick that nut. 1, 2, 3, 4. Pitch is 0.1. Torque is 20,000. friction there, and there you see, so easy. And you can run it again. But because of time, we're going to move on to my PowerPoint slide. And anytime for any questions, we have 7 minutes. We're on time. There are my contact details. If you have, I think every question here is basically in English, so I can go through them very slowly. So if you bear with me, guys, if you have any questions, if you would like to come back to us afterwards, you have my contact details here. You also have contact details of your local representative as well. And I'm simply going to go through some of the questions here. How does it recognize? Okay. Okay, so I have a question here. How does SimSolid recognize the bolt? It recognizes by the shape. It recognizes it's got a bolt head and it's also got a shaft. So it's very clever, and it recognizes that purely on geometry. And then the next one I have here on that presentation, I simply only applied a gravity load. Just to show you how fast it is. Applying loads is pretty straightforward, just like Nastran and Autodesk. I only applied a gravity load and it took the weight of the object into consideration, and that's how it worked. Okay, now I do have a costing here, but I think it's a delicate subject. I mean, we have English prices and we have Euro prices, so I think the best thing to do here is just send me an email and then we can give you a price. I only know the prices in UK in pounds, not in euros. And I also have another one. Okay, the other one is when you use symmetry constraints in Nastran, I guess you're talking about, are you talking about frictionless constraints or are you talking about X, Y, and Z symmetry? Can you quit the part in assembly mode or have you each part? That one. Okay. When you are creating symmetry and when you want to chop the assembly into half, do not cut it in half in the part mode because that's a lot of work. Cut it in the assembly mode and then you should be able to recognize that inside Nastran. I hope that answers your question, Stefan. So I'm just going to hang fire for a couple of more minutes. You're welcome. But if that was a lot of information taken, we will make it available. We will as a PDF. If you liked what you see, please get in touch. But I'm more interested also. I don't know how many people, obviously the people who are spending more than a day might be curious to see how much time it would take in something like this. And I do appreciate your time, guys. Normally we have these sessions in the morning, so I think from next time we'll probably go back to morning sessions. Couple of minutes. I have another question here. Does SimSolid do thermal analysis? The answer is yes. And one more is just come in. Is it SimSolid a multi-user network license? Does that, in other words, can more than one person use it? Well, not at the same time, but anybody can use it one at a time. So so you could have it installed on all the machines and one person can use it at one time. Unlike our Autodesk solutions where everything is named user now, but this one is still network license. Okay, I think I'm going to finish 3 minutes early. First of all, I would like to thank everybody for their time. If you have any questions, please get in touch and I may hear from you guys in the near future. Thanks again for your time, guys. Have a good afternoon, morning, and evening. Bye for now.